Hello everyone. As requested by a lot of students, today I'm going to make a short video about injection, surjection, and bijection. Hopefully it's going to be short. So the definition, F is injective or 1-to-1 if every Y in B is your codomain, there is at most one X in A for which f of x equal to Y. For surjectivity is at least one in your domain such that f(x) equals to y, and for bijectivity it's for a function being both injective and surjective. The second definition here are the ones we normally use to prove a function is injective, surjective, or bijective. Okay. The second one, as I mentioned in tutorial as well, it's the most common one we use when we prove injectivity. It states that for every x1, x2 in your domain, f of x equals to f of x2 implies x1 equals to x2. And its counterpositive, which is this one, is being used very common as well, but the most common one is the second one, so please make sure you know this definition. For surjectivity, we usually need to prove for surjectivity it means your image equals to the codomain, but the other definition is that for all y in B, which is your codomain, there exists x in your domain such that f of x equals to y. Okay, so this is one we used most common, so please make sure you know this definition as well. Now if we look at those four diagrams, you should know that the first one is not injective because for this element you have two, okay, if we call this A, this B, you have two elements in A that map to the same element in B, so it's not injective. Well, if you notice that it's not surjective as well, because there is one element in B that has no element in A that map to it. Okay, so it's not injective nor surjective. For the second graph, you'll see that it's not injective because this element has two elements mapped to it, so it's not injective. But it's surjective because all the elements in your codomain that has some element in your domain that map to it, so it's surjective. For the third graph, you'll see that it is injective, okay, because each of the no element in your domain that map to the same element in your codomain, so it's injective. But it's not surjective because this element has nothing mapped to it. The last one is bijective since it's injective and surjective. Okay. In tutorial, I have a student ask me how do I prove a function is bijective? Well, to prove a function is bijective, you need to prove it is injective and surjective. Now, if we look at this function, the function that everyone is familiar with, f of x equals to x squared, okay? If our domain and codomain is from real to real, you'll see that we have two elements in your domain that map to the same element in your codomain, okay? If you look at the graph of a function, then you can do horizontal line test to test if it's injective. Well, if we do horizontal line test right here, we know that it's not injective. Also, you'll see that if we pick a y here, then there is no x that map to it. So it's not surjective as well. However, we can make this function injective or surjective or bijective by changing its domain and codomain. So if we look at the second one, we changed its codomain to 0 to infinity. And it's going to be the same graph, except this time we only need this part. Not only need this part. Your codomain is only this part, okay? Only this part. So in this case, well, it's still not injective because it doesn't pass horizontal line test, but it is surjective. Well, because every single element from 0 to infinity has an element or one or two elements that map to it. For the third one, we restrict its domain to 0 to infinity, which means we only look at this part. Well, if you look at this, we do horizontal line test. It is injective. And every element starting from 0 to infinity has one element mapped to it, so it's surjective as well. Surjective. Because, well, it goes to infinity, okay? Now we can work on the 30 questions I gave to you if you are my student.